Morning session will be by María Inés de Frutos-Fernández, who will speak about her joint project about formalizing polynomial laws and the universal divided power algebra.
Hi, thank you for the introduction. So this is a joint project with Antoine Chambert-Loir, where we are formalizing in Lean some objects that are important in modern arithmetic geometry. In this area, as well as other areas of mathematics, it is often common to define objects by using universal properties. So what I mean by that is, instead of giving a concrete definition of the object, you just characterize it by some properties that this object must satisfy. So one example will be, if you consider the algebra of polynomials in n variables over a certain ring R, this can be defined as the universal free commutative and associative algebra over R over a set of n generators. And this has the universal property that if you have a map of rings from R to S, and you also have a collection of n elements inside the ring S, then there is going to be a unique map from the polynomial algebra over R to S that extends the original map from R and also sends each variable xi to the element si. However, having a description in terms of universal property is sometimes not enough to fully understand the object that you are defining. Like, for example, if we want to prove that the polynomial algebra is a free module over R, you cannot do that from the universal description. You have to do some concrete description of the polynomial algebra to do this. So in our object, we are formalizing, in our project, we are formalizing some universal object called the universal divided power algebra. And the setting here is we have a commutative ring R, we have an ideal I inside R, and we have a family of maps from the ideal to itself indexed by the natural numbers. We are going to say that this family is a divided power structure if essentially it satisfies the same properties as the family of maps sending x to the n over n factorial. So what I mean by that is, for example, for this family we have this expression here, which is a way to write the binomial formula without using binomial coefficients, right? So we have, if you consider the formula for x plus y to the n, you can rewrite it by putting the n factorial as a denominator here, and then you get rid of the coefficient, the binomial coefficient that otherwise you will get on the right. So for this notion of divided power structure, we generalize this formula. So we replace the x to the n over n factorial by some function gamma n. And similarly, you have some other axioms corresponding to other operations, and if your family satisfies all of these axioms, it will be a divided power structure. Now, if you have an R module M, you can define something called the universal divided power algebra. So this is going to be a triple consisting on a ring, an ideal inside this ring, and a divided power structure on this ideal, such that this triple satisfies some universal property. Now, the definition of the universal divided power algebra is quite technical, so considering the time that I have, I'm not going to try to define it here. This definition is due to Roby. It's used in modern arithmetic geometry, but very often it is used as a black box. So you just use the properties that it has, you don't care about the concrete definition. It is a very important tool in modern arithmetic geometry. So this is used, for example, by Berthelot to develop the theory of crystalline cohomology. And it's also one of the ingredients that are needed to define the Fontaine period ring B-cris, which is used in p-adic Hodge theory, and it's also used to compare between different cohomology theories. So if we want to be able to formalize these results from arithmetic geometry, this is one ingredient that we need to formalize first. As I mentioned, this is something that many mathematicians treat as a black box, so not many people have perhaps read the proof where this construction is done fully. And it's perhaps fortunate that we decided to formalize it, because in the formalization project, we found a mistake in the original construction by Roby. So if you are curious, this dates back to a paper of Roby from 1965. This is the only full construction of the universal divided power algebra in the literature. And if you go to lemma 8 of this paper, there is a mistake there. So the mistake is Roby here is claiming that these two algebras are, these two algebras are isomorphic. But in fact, this is not true in general, because he forgot to tensor with R here. So he's quoting a result from a previous paper of his, and in the previous paper the result is correct, but then when he quotes it, he forgets to tensor on the right, so this is not correct anymore. And then, because this breaks the proof of lemma 8, and lemma 8 is later used in the rest of the paper, this breaks the rest of the proof. However, the final result is still correct, and the main idea of the proof, which is reducing to the case of a free module over the integers, is still the fundamental ideal, and we were able to repair the proof using this idea. We later found out that a sketch of the proof that also avoids this mistake was given by Berthelot and August in an appendix to their book on crystalline cohomology. Okay. So for this construction of the universal power algebra, we have to use some theory of polynomial laws, which I will introduce now. I will start with some motivation. So if you have a function from R squared to the reals, for which there's some polynomial into variables that determines the function, in the sense that f of xy is the polynomial applied to xy for every pair of real numbers, then you can check that this polynomial p is uniquely determined by the function f, and you can also use this polynomial to extend the map to other settings. So instead of taking a pair xy of real numbers, you can take a pair of complex numbers, and then by plugging them into the polynomial, that gives you another complex number. So you get a formula from c squared to c, or more generally, you can get a function from, you could replace the complex numbers here by some R algebra and do the same process. So with the definition of polynomial laws, we want to generalize this kind of functions in two different ways. So one way is we want to replace the real numbers by any commutative ring. And the second way is we want to generalize the domain and the codomain of this function. So yeah, here I have the informal definition of polynomial laws. So we have a commutative ring R, and we have two R modules M and N. So a polynomial law from M to N is going to be a family of maps. So for each R algebra S, we get a map from S tensor M to S tensor N. And then these maps have to be functorial on S. So meaning that if we have two algebras S and S prime, we have a map from S to S prime, then this compatibility property has to be satisfied. Now, from this definition, it's not clear why we are calling this a polynomial law, but it turns out that this is, again, determined by polynomials in some sense, because if you take any finite family of elements inside M, then there's going to be some polynomial associated to this family that's going to determine the value of the function fs in the elements of the form xi tensor mi. And because of this connection with polynomials, we have notions of coefficients, of homogeneous polynomial laws, and of differentials and partial derivatives of polynomial laws, which we have formalized in Lean. Now, I'll show you the formalized definition, and then I will make some remarks about how these two definitions are a bit different. So in our formalized definition, we have a structured polynomial law that has as parameters a commutative ring R, and then two R modules M and N. And then the structure has two fields. So the first field is the collection of maps. So for each R algebra S, we have a map from S tensor M to S tensor N. And then the second field is just the compatibility property that these maps have to satisfy. Okay. So the first point where these two definitions differ is in using rings versus using semi-rings. So in the informal definition, I said that R is a ring, and all of the R algebras that appear are also commutative rings. But in the formalized definition, I'm actually saying that R is a commutative semi-ring, and similarly, I'm saying that all of the R algebras that appear are commutative semi-rings. So we did this because in Mathlib, we often try to generalize results to commutative semi-rings or to semi-rings whenever possible, instead of restricting to rings. But then this brings the question of whether the two definitions agree if you start with an actual ring R. And the answer is yes, because if R is a ring, then any commutative R algebra is again going to be a ring. And we can put the commutative ring instance on S, as I'm showing you here. The only issue is that if the algebra that you started with was already a commutative ring, then this instance is not going to be definitionally equal to the one that you had before. So they are propositionally equal, and so sometimes inside of proofs you have to do some work to check that these instances are actually the same, because definitionally they are not. The second issue in the definition has to do with universes. So in the informal definition, I'm saying that I have a collection of maps for all R algebras. Of course, this is, if you are not careful, you are going to run into some sort of Russell paradox when you try to do that. So the way that we do this in Lean is, if our ring R lives in some universe U, then when we define the fields to fan prime and iscompat prime in our definition of polynomial law, we put all of the R algebras living in the same universe level. But we later were able to extend this to all universes, and the way we do this is, if now we have an R algebra S in some universe V, well, the mathematical reason that this extension is possible is that every element in the tensor product S tensor M is going to be a finite sum of elements of the form Sj tensor M Mj. So that means that we can get this element is going to be induced by some other element in S prime tensor M, where S prime is now a small R algebra. So for example, you could take the subalgebra of S that's generated by this finite family of elements Sj. In our implementation, we do something a bit different. We just take S prime to be some polynomial ring infinitely many variables, which Lean automatically recognizes to live in the same universe as the ring R. And this is not too hard to do in Lean. It was about 200 lines of code, but this is something that is completely overlooked in the paper by Roby. So yes, this is something we had to do. The next slide also has to do with things that are maybe overlooked or ignored when you are writing on paper, but that you have to deal with when you are writing code in Lean. So for example, if we have a ring R, an R algebra S, and an R module M, then at some point in the paper, Roby writes this equality. And he really treats this as an equality, meaning that he starts doing computations on one side, and then he puts that one element on this side is equal to some element on the other side, and so on. Of course, Roby knows that this is not really an equality. These are just isomorphic objects, right? But the point is that the isomorphism is the obvious one. So anyone who is reading the paper will know what the isomorphism is. So Roby is just omitting the detail of the isomorphism to simplify the exposition. So this is just one example where this happens in the papers. It happens more than once. And it happens very frequently, not just in Roby's papers, but also in many papers in mathematics, that this kind of detail is omitted. But when we want to formalize it in Lean, we cannot just omit the details. We actually have to formalize these isomorphisms, and we have to, we have to deal with them in some way. And perhaps the last implementation remark that I want to make is that we wanted to hopefully use some automation in the construction of the proof of the compatibility properties. So what we did is, in our definition of polynomial law, we tried to provide a proof for the iscompat field just by ASOP. So this is an option that Lean gives you when you declare a structure. You can try to provide some proof for one of the fields, and then if that works, then the user doesn't have to provide it. Unfortunately, in our case, this was not very helpful because Lean is only able to figure out the proof for the constant polynomial law. But even in other simple cases, like the polynomial law that is induced by a linear map, where this proof is not complicated at all, this automation didn't work. So it would be nice if we can improve it so that it works in more cases. Okay, so I will just conclude by summarizing what we did. So we formalize a partial construction of the divided power structure in the universal divided power algebra, and this proof that we did avoids the error in Roby's original paper. In order to do so, we also had to formalize the fundamental theory of polynomial laws, including things like coefficients, homogeneous polynomial laws, differentials, and so on. And our main takeaway from this project is that if we want to be able to formalize arithmetic geometry at scale, we are going to need better ways to deal with this kind of invisible mathematics that shows up everywhere in these papers. And yeah, that's everything. Thank you very much.
So the questions for Maria and Inés. Yes, one there.
So about this invisible mathematics, like when you have this equality that's actually an isomorphism, are there lemmas that you had to change that make use of these isomorphisms?
Yes, of course. So as I mentioned, like there are some parts in the argument where Roby is just like switching freely between one side and the other. And like if you want to formalize that proof, you cannot write equalities, right? Like you have to apply the isomorphisms to get from one side to the other. So yeah, I only put one example here, but in the paper we discussed several cases of isomorphisms that we have to introduce, an API that we have to provide to be able to work with them. Yeah.
Other questions in the audience? So I actually have one question. So perhaps you can say a couple of words about the connection between the universal divided power envelopes and polynomial laws. I mean, there.
Right. So yeah, I really didn't go into any detail about the universal divided power algebra here, but one of the things that you can prove about it is that it is a graded algebra. And if you want to understand the graded pieces are going to correspond in some way to homogeneous polynomial laws of a certain grade. So that's the connection, like if you want to move from one side to the other. Yeah.
Okay. Then I also, if there are no other questions, I also ask a second question, which was about the universe issues that you discussed. So is it really needed for you to allow S to be in any universe, or just because you didn't want, I mean, it didn't cost too much and it was nicer to allow S to be in any possible universe level?
Did we actually use it for other universes? Well, I mean, I think we just wanted to have it for all universes, but maybe Antoine also wants to comment. Like, yeah.
Perhaps if we have a microphone.
Maybe there were two reasons. One was just the matter to do it because we have to do it. And the other way is this stuff is going to be used in the formalization of Fontaine's ring, Bicresse, and whatever. And I have no idea in what universe those rings will live eventually.
Yes, this was my question. So if you have thought about
refactor this later on. So.
Oh, there's one question here.
Thanks. So related to this discussion of universes, do you ever have to quantify over all algebras in some specific universe?
I mean, we do here in this definition, right? So
then you have to use universes because you have to then work in a higher universe, right?
Well,
get into, as you said, you will get into Russell paradox issues.
Right. So here in the definition, because of that, we have to choose some universe level for the algebras that appear in the definition, right? We cannot just use type star and let Lin figure it out, because then you run into these issues, right?
Yeah.
So you have to choose a universe level. We chose it to be U, so the same as the universe level for R, so that in particular you could apply this to S is equal to R, because otherwise universes in Lin are non-cumulative, so it will not apply to R. But yeah, here we have to fix the universe, and then later when we generalize this to fan prime to the function to fan, then there we allow S to be in any universe, not necessarily in universe.
Do you have to manually lift to a higher universe? Because Lin does not have cumulativity.
we have to lift it.
Yeah.
Yeah, we explain the argument in the paper.
Okay. So perhaps there are no further questions. So let's thank Maria and Inés once more.